last class we have discussed about how to represent data or how to store data, in what form we will store data. So in that case we have seen that two sorts of storing techniques. That is, one is master, where we plot the cumulative rainfall with respect to the time. So cumulative rainfall in y direction and the ordinates and time in the system, and we can get one graph that can be called as mass card, right? We have seen that thing. And another thing we have seen from the mass card, what are the things there can be clarified. Looking at some mass card, what are the nature of the rainfall we can find out, right? We have seen that one. And other than that, we have seen another thing that is called Hyetograph. And in that case, Hyetograph is basically the representation of the intensity of rainfall with respect to the time. So if the obviously when we will be finding out the data, we will be finding out the data from the suppose non-recording rain gauges. Non-recording rain gauges. In that way, non-recording rain gauges, if you see in a certain interval, you are finding out or collecting the data, you will get the cumulative data directly. You will not get the intensity or change in data or change in rainfall, right? So you will get the cumulative data like this one. So from that, we need to find out what is the change in data or change in rainfall, change in depth in rainfall, and next we have to find out what was the intensity of the rainfall for that time period, right? So after finding out those intensities with respect to time, we can find out or we can plot this sort of a bar chart, right? We are seeing those things in clusters. So this bar chart will be called as Hyetograph. Clear? Now, next we will be having what will be the average rainfall. As because already we have seen or already we have discussed that one rain gauge station will not be enough to say what is the rainfall in a particular area. We have already seen that, right? So we have taken an example like as because we are having one rain gauge in our lab as well. So looking at the rain gauge or looking at the data of the rain gauge, I cannot say that this is the amount of rainfall in overall Durgapur or overall this Balgaon district or something, right? So we cannot say that looking at one station data. So we have to install several sets of data or several sets of rain gauge stations in various places in a particular area. That is called the networking, right? We have already seen that rain gauge networking. So in a particular area, suppose you are having 10 or more than 10 or whatever it is, whatever the number may be, you will have different sets of data. Yeah. So in Durgapur, suppose you are having 4 mm of rainfall today, right? But in Assam, you are having 60 mm of rainfall. So overall, in this district, you are trying to find out what is the rainfall. Then what you have to do? You have to average it, right? You have to find out the average. Clear? So average from all the rain gauge stations in your catchment area. So what will be the system to find out the average rainfall? That is, there can be several methods, like 3 methods are there. One is called arithmetic mean method. Second one is called Thiessen polygon method, and third one is Isohyetal method. Clear? Here, 3 methods are there. We will be discussing those 3 methods, that how that works. First of all, arithmetic mean method is a simple one. Suppose you are having n number of stations in your catchment area, and with respect to the n number of stations, you will get n number of set of data for a particular month or for a particular day or for a particular year. So that precipitation in several stations are supposed P1, P2 and up to Pn. So you are having one catchment area like this, you are having stations installed over there like this one. So sum up all the precipitation values or depth of rainfall and divide the number of the rainfall stations. Simply you are finding out the average. So that is one process by which you can say that is the average rainfall in that particular area. It is simple, right? It is the simplest one. So the mathematical representation will be like this one, that average rainfall P bar will be equals to P1, P2 up to P1 Pn divided by number of stations n, and that can be expressed by that equation as well, that is summation of Pn Pi, where I will vary from 1 to n divided by n. Clear? Simple? Simple to it. Nextly, we are having this one, that is called Thiessen's polygon method. Now what is the problem over there is that we are not giving any sort of weightage. Suppose in a particular station, this station, in this zone, suppose the rainfall was higher. In that particular zone, the rainfall is suppose higher. But what we are doing, we are summing up all the values and we are dividing with the n and we are getting the average. So I am not giving any sort of weightage to that particular station. Right? Though it is having some extra weightage because it is, suppose it is nearby no stations are there. Nearby no stations are there. So it is covering the largest area. So to give some weightage to it. So I will give some weightage with terms of or with respect to the area it is covering. Here, weightage with respect to the area it is covering. Right? So how we can find out what is the area it is covering? That is a process. Describe the things. Right? How to find out that one? That is, draw the catchment area to the scale and mark the rainfall stations in your map. So first of all, draw the catchment area with scale, spherical scale, and mark those catchment rainfall stations like 1, 2, 3, 4, 5, 6, 7, 8, whatever it is, right? And we can consider the rainfall stations which are outside the catchment area as well. Here, we can consider in this case you can see that 1 and 3 and 5 those stations are outside the catchment. But we can take the data from 1, 3 and 5, right? We can take the data and it is covering, maybe it is covering some portion in this catchment area as well. So we have to consider that portion also, right? How we can do that? Secondly, we have to connect all the rainfall stations with a straight line. So I am connecting all the stations with a straight line. Third step will be to find out the bisectors, perpendicular bisectors of those lines. So those were the lines, right? Those were the lines connecting all the stations, and I am finding out what is the bisector, and I am trying to find out what is the perpendicular bisectors of each and every line. So this one will be the perpendicular bisectors of this line, this one will be the perpendicular bisectors of this line, and so on. So I am finding out the green lines are basically the perpendicular bisectors of the blue lines. Blue as line. Here, so what will happen if we try to, if we elongate up to this point and these bisectors from this line, this is a perpendicular bisector as well, and I am getting another perpendicular bisectors from this line, and they are meeting at a particular point, right? So we have to elongate those perpendicular bisectors such a point where those bisectors, perpendicular bisectors will meet each other, right? So in this point, this and this perpendicular bisectors are meeting. In this particular point, these perpendicular bisectors, this and this perpendicular bisectors are meeting, and so on, right? So we are finding out the perpendicular bisectors first of all, and we are extending the perpendicular bisectors so that they are meeting at a particular point. Clear? Up to this it is okay? Clear now? The polygon, you can see some polygon formed over there. The green line polygon, right? Some polygons are formed by the green lines, perpendicular bisectors. Those polygons formed by the perpendicular bisectors are influenced area of those particular stations. So if we consider station number 6, as because you can, I have already told you that nearby no stations were there. You can see a larger area is covered by 6 number of stations, right? So this will be the polygon area, or this polygon area will be dedicated to this 6 number of stations. 6 stations. Clear? Now, one thing you need to understand that whenever we are trying to find out the polygon area, we cannot select the area outside the catchment area. So the boundary of the polygon area will be equals to either these perpendicular bisectors, or if this extended to outside the catchment area, we will consider up to this boundary of the catchment area. So for 6 number of station, this one, this and this will be the influence area or polygon area of the 6 number of station. Similarly, for 2, we can see this is the boundary, this is the boundary, this is the boundary. Now it is going outside the catchment area, but obviously we will not consider outside the catchment area. So this boundary of the catchment area will be the boundary of the polygon for 2 or second catchment rainbow stations. Clear? Clear? For 1, what we have for 1, 3 and 5, because those are situated outside the catchment area. For those cases, what will happen? So for 1, the influence area or the polygon area will be this and outside the boundary of the catchment area. So this will be your influence area for 1 number of stations. We will not consider up to this point, as because we are finding out what is the average rainfall in this particular catchment area. Clear? Now we have already found out what is the influence area. Suppose the influence area for 1 is A1, for influence area for 2 is A2, and so on. Then what will be the formula? The formula will be like this one, where the average precipitation for those cases will be equals to P1 multiplied by A1, P2 A2, summation of all the P multiplied by influence area divided by the total area, that is A1 A2 A3, and obviously summation of this total will be equals to A, which is area of the catchment. Obviously you are not going outside the boundary, so total area forward will be the area of catchment area, nothing else. So if you represent this formula in this format, then PI summation of PI where I will vary from 1 to n divided by summation of AI where I will vary from 1 to n, and this is nothing but A. This is nothing but A. Here. Okay? So summation of this where PI AI by A, where I will vary from 1 to n. Clear? As because this is nothing but clear up to this. Okay. Now we are finding out. You can see one ratio we are finding out. AI by A. AI by A. This so this is the way how we can find out the average rainfall in Thiessen's polygon method, right? Where we are finding out one ratio of the area, influenced area of a particular station divided by the total area. Clear? And we are multiplying with the precipitation data of that particular rainfall station, and we are summing up all the effective ratios. Clear? Okay. Now third method is the Isohyetal method, where again we will plot the same or any sort of catchment area in scale, and we will take various sorts of, even we can consider here also, we can consider the data from outside the catchment area, right? So we have pointed out all the rainfall stations. Clear? Next, what we have to do? Next thing, we have to find out the isohyetes. Those lines are called isohyetes. Now, what is isohyetes? Isohyetes are drawn considering the rainfall values at the station and using suitable interpolation scheme. Now, isohyetes are nothing but the points joining line. Obviously, this is an imaginary line joining all the points which is having same amount of precipitation. Yeah, like contour line, exactly, like contour line, right? Here also, obviously, you can see from A and E. In E, the precipitation is 28. In A, the precipitation is 32. In F, precipitation is 46. B 42. Now, if we try to find out the 30 precipitation line, isohyet line, where all the points will be connected by the 30 precipitation is there. Now you can see from A to E, in between somewhere here 30 will be there. From E to B, somewhere there 30 precipitation will be there. From E to F, somewhere here 30 precipitation will be there. If you connect with a smooth line, you will get 30 precipitation line, that is Isohyetal line. Again, 40 will lie in between 32 and 42. Will lie between 28 and 46, and if you connect those lines, and again will lie in 28 and 42. If you connect all the points, you will get the isohyet lines of 40. Clear? We have already discussed that how we can find out the isohyetes of 30, 40, 50, 60 and so on, right? We can find out the isohyetes. Now again I am saying we cannot go beyond, whenever we are finding out the effective area or influenced area, we cannot go beyond the catchment area, because we are finding out the average length of the particular catchment area. So we will calculate or give some weightage with respect to the catchment area only, right? But obviously, for the data perspective, you can take the data or you can use the data outside the catchment area. That can be okay, right? So we have got the idea how we can find out the influence the isohyetes line, and this can be one number of questions there can be. That is what is isohyetes line. So isohyetes line is nothing but the imaginary line connecting all the points which is having same amount of rainfall, right? So area between two adjacent isohyetes are measured. So two adjacent isohyetes area will be measured. I have already shown you this figure that we have to find out the area between two isohyetes line, and obviously we cannot go beyond the catchment area. So for the two adjacent isohyetes line 30 and 40, the area will be equals to this one, where the boundary line will be this, right, to this one. So this will be your area between the two isohyetes 30 and 40. For 40 and 50 it is easier, as because this will be your boundary line, this will be your boundary line, and as because these are the boundary line of your catchment area, those will be the boundary line. So the influence area of between those two isohyetes line will be equal to that one. So area between two adjacent isohyetes are measured using a diameter. Obviously, to to find out area, arbitrary area, any sort of arbitrary area, you need to use some instrument that is called planimeter, right? So, using the planimeter, we can find out the area. If the isohyetal go outside the catchment boundary is used to bounding line, right? I have already told you that if it is going outside the area, the catchment area boundary line will be treated as the boundary. Now, as because we have got, suppose up to Pn number of stations are there, so P1, P2, Pn will be the data or precipitation data in the catchment area, and the area between two isohyetal lines. What will be the number of areas between two isohyetal lines? If n number of isohyetal lines are there, if n number of isohyetal lines are there, then what will be the number of area between two adjacent isohyetal lines? N minus 1, no? N minus 1. So here you can see, suppose this is one catchment area, isohyetal line. So 1, 2, 3, 4, 5, and obviously suppose 6 number of isohyetal lines are there. So you can see this is one area, second area, third area, fourth area, and fifth area. Right? So number of area between two adjacent lines will be equal to n minus 1. Whereas when suppose P1, P2, Pn values are isohyetal values, and A1, A2 up to An minus 1 are the intermediate area of the isohyetal line, then this will be your formula where P average will be equal to area 1, which is in between P1 and P2. So area 1 will be multiplied to P1 plus P2 divided by 2. As because we can consider that here 30 precipitation was there. So in between average rainfall has occurred, right? Average rainfall has occurred. So the rainfall can be P1 plus P2 divided by 2. Simple. So we are multiplying this average precipitation with the effective area. Again, P2 plus P3 by 2, that is the average area between the second isohyetal line and third isohyetal line, and that will be multiplied by the second area, influence area, right? And so on, we will get this one and divided by total area, because we need to find out the precipitation only. We have already given out the weightage, so we have to now divide the area, because already we have multiplied that area. So we have to divide the total area. We are dividing the total area and we are finding out this one as simplest form. That is, average precipitation will be equal to 1 by A. If you take outside this A area, total area. Again I am saying, total area A1, A2, A3 up to An minus 1 will be equal to the area of catchment, nothing but the area of the catchment volume. So this will be represented by A. It is nothing but A1 plus A2 in this case, plus in this case this one is A, total area, right? So if you take outside this one, so this will be summation of AI Pi plus Pi plus 1 divided by 2, where I will vary from 1 to 10, right? Clear? Is there any confusion regarding three methods? We have seen three methods. First one was easy, that is to find out the average precipitation by simple formula, that is simple find out the average. Secondly, we have to find out the average precipitation using Thiessen's polygon method, where some polygons is to be constructed. How we can construct that polygon? First of all, you have to join all the rainfall stations with a straight line. Then you have to find out the perpendicular bisector, and you have to extend the bisectors so that they will meet at a certain point. that we create the polygons that will be the influence area, that will be considered as the influence area of the stations, and ultimately we can find out the precipitation by this formula. Similarly, in this case we need to find out the isohyetal lines, where isohyetal lines are nothing but the lines which are connecting same precipitation. So we will find out various isohyetal lines, and we will see what is the area between two isohyetal lines. So finding out that one, we can find out the average precipitation by this formula. Those are the three things we have learned today. Is there any confusion regarding these methods?